where we left off the other day was in how to change equilibrium, Le Chatelier's principle. And I actually think I need to do this first. Okay, so I'm putting up a website that allows you to look at ways to change equilibrium. We're not quite done with the one we were working with, but so I leave this up for you guys. So it's on it'll be on the lecture video. But this website allows you to determine what's going to happen if you disturb a chemical equilibrium. So it gives you a K. A simple reaction, A plus B makes C plus D. It gives you the equilibrium constant. And it allows you to adjust your parameters. So let's say I start with no C and no D, and I equilibrate. Okay. Well, I notice that my concentration of A and B go down. My concentration of C and D goes up until it reaches what we call in chemical engineering steady state, or equilibrium. Our concentrations are no longer changing. Does that mean the reaction has stopped? No, it's still going back and forth. Now, I can change one of my parameters. So which one should I change? A. Should I make it more or less? More. So if I add more A, I add a bunch more A. Which way is the reaction going to shift? I'm adding A. So the reaction is going to shift right. So eventually I should end up with more C and D. Well, let's see if that happens. All right. So did I get more C and D? Yep. So my A went up dramatically because I added in A. And then both A and B went down a little bit as it reacted, and I get a new equilibrium with C and D. So the reaction shifted right. So if you're a little bit confused about how these things work with equilibrium, just go to this website and play around with it a little bit. All right. So now we get back to here. And all right, where we left off, we had added N2O4, saw the change in equilibrium. What happened here? We added N2O4. Now, we changed our equilibrium again. Talk to your tables. What do you think could have happened at this point? Griffin color? Irresistible. Reddish purple? Yeah. I'm going to go with like a deep red. All right. So what happened at this point? Talk about it at your tables. What could have happened at that point to reestablish equilibrium? All right, so who's got an idea? Yes, Griffin. Take away some energy. Okay, so let's see. This is N2O4, and this is NO2. So if delta H is greater than 0, we realize that energy is a reactant. So if energy goes down, which way is the reaction going to shift? It's going to shift left, which means my N2O4 is going to go up, my NO2 is going to go down, so that works. That means if you drop the temperature, this will work. There is one other way. If you add the answer is if you added both, then both of these lines would go up. What's one other way we could shift the equilibrium? So if we took away NO2, then N2O4 would also go down, right? Because if we took away NO2, the reaction would shift right. I want you guys to get this. Keep thinking. Volume. So if we change the volume, the other way though, we have 1 mole of gas. Oh no, you're right. If we have 1 mole of gas in our reactants and 2 moles in the products, well, if we drop our volume, compress the container, it's going to shift to the side that has fewer moles. So we could have either made the volume go down or make the temperature go down. Either one would do that. Okay. So this is sort of a key idea. You can expect this, if not on problem sets, then on test quizzes. This graphical representation. So again, when you add in one thing, it's going to shift the other direction. If you take it out, it'll shift in that direction. And then you can change temperature or volume. Okay. So now we're going to do equilibrium calculations. We can do lots. We can. Who was that? Did I hear a phone? Or am I just hearing things? I'm going insane. I could have sworn I heard, whatever. It's okay. Can you guys just tell me you were defending one another and that I actually did hear it? And God damn it. Oh well. I had a good run. All right. We can and will do a variety of calculations based around the equilibrium constant for a reaction. A lot of what's left in this year. I was thinking about it. You know, we're done with we're going to be done with 15. That means there's only 16, 17, 18, 19, 20, 21. 6 left. So you guys are probably only going to get one more lecture the rest of the year in this class. So, all right. The simplest type. If I give you the amounts of reactants and products present, which way will the reaction proceed in order to reach equilibrium? This is your Q versus K, where this is temporary and this is equilibrium. And then, like I said, if Q is less than K, it proceeds to the right. If it equals K, it's at equilibrium already. If Q is greater than K, the reaction proceeds to the left. So let's try this and see how it works. All right. We have this reaction. N2 plus 3Cl2 makes two NCl3s. The equilibrium constant at 100 degrees C is 96.3. So Kp changes with temperature. That's the only way to change your K. Okay? The only way to change your K is to change the temperature. So suppose that in a reaction vessel at 100 degrees C, the partial pressures of each gas are as follows. In which direction will the reaction proceed? So on the next spot right here, I want you to write down your equation for Q and then solve for Q. So try to do that with your partners at your tables. Try to solve for Q. So I actually want you to write down the equation. Go back in your notes for Q. Very close. All right. So your Q is products of reactants. We're using pressures here because I gave you Kp. So it's the partial pressure of your product. Why do we put the 2 here? The coefficient of the product. On the bottom, we have pressure of N2 times pressure of Cl2 cubed, again, because of the coefficients. So I'm going to depend on people with calculators for this because I wrote it down this far, and that's as far as I got. Mm-hmm. Okay, so the question was, if we have a decimal for pressure, like we do for Cl2, and we're cubing it, doesn't that mean it makes less of an impact? Is that well? So it actually it ends up making more of an impact because you're cubing it, and that's going to be smaller and smaller and smaller. So which direction would that imply the reaction needs to go? Yeah. Mm-hmm. All right, what did we get for value? So we'll just say 145. Now, 145 is greater than 96.3. So which direction will this go? Will it go to the products, reactants, or is it at equilibrium? You can either look on the previous slide. Yeah, Ian. Wait a minute. Yeah, it says to the left, but I'm not buying it. According to the sheet, it says to the left. Hold on, let me think about this for a second. I think that sheet might be wrong. No, this is right. Sorry. Yep. So it's going to shift to the left to make more reactants. Right? So that makes sense because my numerator is too big. 145 is greater than 96.3. My numerator is too big. In order to get back to equilibrium, I need less numerator and more denominator. I need less products and more reactants. I'd rather have you think about it that way than memorize that list from the slide before. If your numerator is too big, you have too much product. If your denominator is too big, you have too much reactant. I think it's easier to think about it that way than it is to actually memorize, like, oh, if Q is greater than K. Okay. Now we get to the fun stuff. So more K calculations. And here's where we're gonna get to do some algebra. Yay. A slightly more difficult calculation is to find K given some information about the concentration of reactants and products. So now we have this same equilibrium, but we have moles of N2 and moles of CO2 added to a container. Okay. How much NCl3 do we have at the beginning? If we're just adding N2 and Cl2. How much of this do we have at the beginning? 0. The reaction hasn't started yet. So initially in my vessel, I have none. So at equilibrium, I have 0.44 moles of N2. Find Kp for this reaction at 200 degrees C. So this is a new temperature. It's hot. So the Kp will be different. All right. So what do we need to be able to do to find this? For this type of question, we will be using Rice charts. And this is the skill that you need to get in this chapter, because we're going to do it again and again and again and again and again. Lots of Rice charts for the rest of the year. Ask your friends who have taken AP Chem in the past. I hope they remember these Rice charts. Sometimes in college, you'll hear them called ICE charts. They'll just take the R out. I was talking to some students who came back to visit, and they're like, oh yeah, we did ICE charts all the time. Or like Rice charts, but so they felt well prepared. So R is your balanced chemical reaction. You need the balanced chemical reaction for the coefficients. I is your initial amount. C is your change. So you can also think of it as coefficients. Think of this as your delta also, because you need to pay attention to the coefficients when you do this part. And E is at equilibrium. So the amounts can be moles, molarity, partial pressures, anything that's proportional to moles. Not grams. However, this is true. In our charts, we can have moles, molarity, partial pressures, whatever. But our equilibrium expressions, like I said before, are only molarity or partial pressure. So you can use these sort of charts using moles, but eventually you're going to have to go to pressure or concentration. So let's set one up together. And I'm going to leave some space up above. So what is my balanced chemical reaction? What am I going to put in this line right here? All right. You don't have to put the lines in, but you know, if it helps you. I also tend to do a line between products and reactants. Now, we have options. Bless you. Griffin, what color are we going to use now? John Quill? I was going to say white because like a quill, maybe like a grayish. All right. All right. Because I'm thinking of like a feather. So we said that we can use moles, molarity, pressure, whatever. What did they give us in the problem? What unit? Moles. Now, eventually we're going to have to convert it to concentration or pressure. So ideally, we'd want to use either this or this. I am actually going to end up using concentration. I derived earlier in the notes how to convert between Kp and Kc, right? So I'm going to do this in concentration. So if I look back at my numbers, I have 2.7 moles of N2. What's my volume? 50. So what's 2.7 divided by 50? For those of you who have calculators or can do mental math really well. It's like 0.0. Yeah. So my concentration is 0.054. All right. Now, what's my concentration of Cl2? Somebody with a calculator. Yeah, Sophia. 0.17. Okay, so now I introduce this into the container. A reaction happens. As this reaction happens, what's going to happen to my reactants? Concentration of my reactants decrease, my concentration of my products increase. Now, if my concentration of N2 goes down by X, how much does my concentration of Cl2 go down? How much does my concentration of NCl3 go up? Coefficients. Watch your coefficients. Right, so this is just stoichiometry at this point. Okay, now what am I left with? What else? What other piece of information am I given? Yep, so turn that into a concentration. And what do I get? .0088. So now that seems one of these is off. I think this should be 0.054. Check out my math on that. Okay. Thank you. You guys can always call me out on that too. Or please, not can. Please call me out on that when I write down things wrong. So now, what is my X value? How do I figure out? This is my delta, right? How do I figure out what X is? Subtract. So 0.054 minus 0.0088 gives me what? So that's how much it changed for N2. How much would it change for Cl2? Well, I do that times 3, which is 0.1356. Okay, so did I do that math right? And then this would just be double, which would be 0.0904. So you were given the following information. Or you were given these three things, and you can solve for the rest. Yeah, Thomas. So where did I get 0.0452? This came from the difference between my initial N and my final N. So this was given to me in the problem. So I know that if I started with this much N2 and ended with this much, I know how much it had to change. I know how much reacted. So if that much reacted of N2, 3 times that much had to react of Cl2 because of the stoichiometric ratio, and then 2 times as much had to be made because of the stoichiometric ratio. So that's C, you look at the coefficients. So N2 and Cl2 reacted. We know how much N2 reacted, which means we know how much of the other things reacted as well. Okay, so now, next color. Vanilla ice. Is there a terrible color? Yeah. Heliotrope. I'm going to go with yellow doesn't show up very good. Orange, yeah, good orange. For the sun, I think of helio as like helium and from the sun. Okay, so now I have my Kc is equal to the concentration of NCl3 squared N2 Cl2 cubed, and I don't remember what these numbers were from the previous slide. What was my concentration of NCl3? It was like 0.0904. And then what was my N2? And then Cl2? 0. All right. So this, when one of you guys solves for this, we'll get, or a couple of you solve for it, so get independent verification of the answer. That was real, right? That happened out there, screaming. Okay. 25,094. Let's see if we get independent verification. Yeah, I hear a lot of keys being tapped, but I haven't got another answer. Okay. Wow, 3 different answers. Okay, so our calculator skills, we need to... $22,813. What'd you get, Joanna? 4 different answers. What'd you get? How many chemists does it take to solve 22,812? I'm going to go with 22,812. I have multiple. So what I've learned from this is that we need to learn to use our calculators better. Okay. Make sure that if you're using your calculator, put this in parentheses and this whole thing in parentheses. Make sure you get it right. Okay. So now though, what is it? Go back to what the actual question asked. What did the actual question ask you for? Did it ask you for Kc? It asked you for Kp. So we have an equation. I'm not sure. It might actually be on your blue sheet, but I'm not positive. The Kp-Kc connection. If not, we derived it earlier on. All right. Okay, so I'm not going to make us go back. Kp equals Kc RT delta N. So I want you guys to solve. See if you can solve for Kp. I'm going to solve for it too. I did. Are you going to be around for a little while? Yeah. Can we come back like third lunch? Yeah. Do you want to get? Do you want to get on the lecture?
She's on. Yeah, I'm on all the lectures.
Well, they're all new now. Yeah, they're all new. So that's Gina, everybody. Gina and Marianne. Gina's been erased. So yeah, come back in like 20 minutes. I'll have free time. Awesome. Okay. So, where did we get all of these numbers from? So, 473 is 200 Celsius in Kelvin. Remember, this is gas stuff. We want to go to Kelvin. The -2, where did the -2 come from? Delta N is -2 because it's number of moles of gas in the products minus number of moles of gas in the reactants. So I had 2 moles of gas in the products, 4 moles of gas in the reactants. I get -2. So really what this is 22,812 over (38.7) squared. The question is, why am I dividing? Well, anything to the -2 just means it's inverted. So all right. Woo. Last page. Yeah, Wesley. So the question is, what does this number tell us? This number tells us what my equilibrium constant is in pressure at this. No, this is the at any. No matter where I start with this reaction, at 200 degrees C, I'm going to end up with my pressure of NCl3 squared over my pressure of N2 times my pressure of Cl2 cubed to be this number. So this is where that ratio will eventually end up. So this is where the just think of it, this is where the reaction wants to go. It wants to go to this number in terms of a ratio. Great question. Is this a pressure in terms of some sort of unit of measurement? This is a dimensionless number. So essentially we say it has no units. You'll see that a lot in science. They'll like make these dimensionless numbers to help you understand stuff or confuse you a little bit. But the more practice we get with this, the more it'll make sense. I feel like this is one of those skills where I'm going to introduce it to you, but until you practice it for a while, it's not going to get internalized. And practice we will. That was my Yoda for the day. All right. So even more K calculations. So that one is somewhat common. This is the most common. You're given the equilibrium constant and asked to determine the concentration of reactants and products at equilibrium. So here's a reaction. SO2Cl2 makes SO2 plus Cl2, and I have a Kc of 6.1. So you're given the equilibrium constant. And now I'm telling you how much is added, and I want to know at the end how much there will be. So this is still a Rice chart, but instead of knowing what my x is, I'm going to have to find out what that x is. So let's go. What's my balanced chemical? Oh, Griffin, new color. I am going to go with pink. The color was buff, so I'm going to give it pink. RICE. So what's my balanced chemical equation? Oh yeah, SO2 plus Cl2. Now, all right. Again, I'm separating my reactants and my products. Now, I can put, because this is a rice chart, I could put the 0.43 moles right here. But what would be better for me to put in directly to my initial SO2Cl2? Yeah, concentration. In this case, it happens to be the same because it's 0.43 moles in 1 liter. What's my initial concentration of SO2 and Cl2? There's a little hint in there. There's one word that tells you. Zero. Why is it 0? Yep. There's a key word there, though, that tells you there's nothing. Yeah, evacuated. So now, as this reacts, we're lucky that we don't have coefficients here. So this reacts, some of it goes away. How much, if I lose X of this, how much SO2 do I gain? X. How much Cl2? X. All right. Whew. So, what's 0 plus X? X. 0.43 minus X is, so at equilibrium, some of my SO2Cl2 has reacted. X amount of it has. And X amount of SO2 and Cl2 has been made. I don't know what that X is yet. But I do know this. I know my Kc value is this. And I also know that this is equal to 6.1. So at equilibrium, this expression equals 6.1. In that space below, in that slide to the where it says even more K calculations, see if you can set up the equation that you're going to use to solve for X. All right, so this is the equation that you should have set up. Is that x squared over 0.43 minus x equals 6.1. So what do we need to solve this? A graphing calculator or the Pythagorean theorem. Right? So 0.1 times 0.43 minus x equals x squared. Now, here's the issue that a lot of you guys are going to have. Sorry, I'm trying to do the math out here as we go. 2.623 minus 6.1x equals x squared. So just going to bring this up here. X squared minus x squared plus 6.1x minus 2.623 equals 0. All right. Now, this is a quadratic, as we can see. On a test or a quiz, we will never give you a quadratic to solve for. One of the reasons why is a lot of you mess it up when you put it in your calculators. people come up to me and are like, there's no solution, or I got negative values, just because you didn't put it in right. Okay. So let's see if we can get some independent confirmation of what this x value should be. What did you get, Edward? 0.403. So that's it's point. I'm guessing other people check. That seems pretty reasonable. Unless you want the negative one, we certainly don't want the negative one. We'd be creating mass from nowhere, which we can't do. All right. Can people confirm this for me? We have confirmation. All right. So now x is 0.403. If we go back, I'll give you guys a second to copy. All right, Griffin, what's our next color? Feldspar. Feldspar is a thing that I should know. It is a mineral of some sort. I'll just make it green for fun. Okay, so now at equilibrium, my SO2 Cl2 concentration is 0.43 minus 0.403. So it's equal to 0.027, right? That's not what I was asked, though. I was asked for this, which would just be 0.0403 and 0.0403. I got this. Hold on, I'm going to come back to the slide in a second, so just stop. I got this because I solved for x, and then I plugged it back in here, right? So once I solved for x, I was able to plug it back in. All right. All right, and the next few slides are just the review of objectives that we'll go through. And then we're done with lecture 15. No. Let's see. Oh, hold that question for a minute. Okay. So, review of objectives. If I gave you a set of experimental observations regarding all kinds of things that are reversible, so you should be able to connect the observations to the reversibility of the underlying reactions or processes. What does that mean? Some of these AP objectives are tough. What do you think, Edward? Yeah, maybe like to what extent it would go. Maybe even, you know, there were some things on problem set 14 that ask you to predict the rate limiting step. Like maybe if you looked at some structures and had to figure out, well, which way would you predict the equilibrium to go? Student can, given a manipulation of a chemical reaction or set of reactions, determine the effects of that manipulation on Q or K. So this just says, this is Le Chatelier. If you change your conditions, what's going to happen to your equilibrium? What's the only thing that can change K? Temperature, right? Everything else would be changing Q to go back to your new K, to your old K. Student can connect kinetics to equilibrium by using reasoning about equilibrium, such as Le Chatelier's principle, to infer the relative rates of the forward and reverse reactions. So that's just guessing. You know, with Le Chatelier, if you change your equilibrium conditions, like you change by adding something in, one of your rates will go faster than the other. That's what that's saying. Woo! The student can, given a set of initial conditions and the equilibrium constant, I can speak, predict whether the reaction will proceed towards products or reactants. That's just comparing Q and K. The student can, given data of a system at equilibrium be obtained, calculate the equilibrium constant K. That's what we did, not in the last slide, but in the two before that. Student can use stoichiometry to determine. Oh wow, these AP objectives are so wordy. Let's try to break this one down. Given a set of initial conditions, concentration, partial pressures, and equilibrium constant K, use stoichiometric relationships and the law of mass action. I don't even know what the law of mass action is. But Q equals K at equilibrium. Oh, I guess that's what it means. To determine qualitative and or quantitatively the conditions at equilibrium for a system involving a single reversible reaction. This is whether it goes left or right, and it's this whole thing we were doing right here. Rice charts, right? Figure out your concentration or pressures at equilibrium. Okay. Last, the student is able, for a reversible reaction that has a large or small K, to determine which chemical species will have a very large versus very small. Well, if the K is large, that means it favors the products. If the K is small, it favors the reactants. Student is able to use this guy's principle to predict the direction of the shift. I feel like you guys are comfortable doing that already. Student is able to use the principle to design a set of conditions that will optimize the desired outcome. This is one we're going to have to look at, I think, a little bit more. And the student is able to connect the principle of Le Chatelier to comparison of Q and K by explaining the effects of the stress on Q and K. So this is what the AP says you should know from this chapter of our story of chemistry. And we're done with 15.